This video is intended to help you find a p-value for any z procedure. I promise you, if you're having trouble with this, there is a systematic way that does make sense on how to find your p-value. So the first thing is you want to record the direction of your alternative hypothesis. The second thing is then calculate your test statistic. Under the normal curve, you'll then find the area that follows the direction of your alternative hypothesis from your z statistic. You want to look up this area with a table or software. Most of us are using tables, but a lot of these tools are going to give the area to the left of whatever you plug in. So you have to always keep that in mind, and that can be kind of the toughest part of this. So it's always going to give you the area below whatever value you plug in. So let's look at a couple examples. First, we want to find the p-value when theta is less than theta naught. That's our alternative. So wait a minute, what's theta? Well, theta is just a general parameter here. I could have used p less than p naught. I could have used mu less than mu naught. I could have used the difference between two proportions. The thing is that part doesn't matter as much. Once we know the alternative and once we calculate our test statistic, the way we find the p-value is identical for any z procedure. So if you got this down, it'll take care of a lot of issues you might be having. All right, so let's look at this alternative. It says theta is less than theta naught. So that less than piece is going to tell us how we find our p-value. So coming from the standard normal distribution, we want to draw the standard normal. And remember, the standard normal distribution has a mean of 0, and then it has a standard deviation of 1. So if we write these in, these are little just kind of places so we can figure out where our test statistic falls, which in this example, our z test statistic is negative 1.09. So that's going to be about right here. It looks like a little less than negative 1. And because we're doing a less than alternative, we're going to find the area that is less than negative 1.09 in our standard normal distribution. So what this looks like in probability notation is we're going to say the probability that z is less than negative 1.09. Well, here's the deal. This is to the left, right? To the left, to the left. It's to the left of our negative 1.09. So when we look this up on the table, whatever we look up negative 1.09 to be, that's going to be our p-value. There's no manipulation necessary. So we look this up, and let's see, I find it right away. I already have my little arrow towards it. That's negative 1.0. And if we cruise across these columns, we can see that the last column represents the hundredths place of 0.09. So I assume that you kind of already know how to use a z-table, but in general, we have our z's over here, z-scores. We have our hundredths place in columns. And so we only go to 2 decimal places here. That's good enough. And we see that our p-value is 0.13786. So if 0.13786, that is my p-value. That's the area below the curve here. So I found it. I'm done. Now let's look at B. By the way, those less than p-values are the easiest ones to find. If we have a greater than p-value, then we need to look at the area that is greater than our test statistic. It follows that same idea. That's the systematic thing that I'm talking about here, is that our p-value will always follow the direction of our alternative. And because we have a greater than alternative, we're going to look at the area that is greater than 0.81 under the standard normal curve. So that's going to be this area here. So we're looking at the probability that z is greater than 0.81. Now, we know that our z-table is always going to give us the area to the left. If we look up 0.81, it's going to give us this area over here. Thing is we don't want that, right? We want the area above that. So what we have to do is we have to use what we know about complements and say, okay, well, I'm going to find the value. If I want to find that area above 0.81, then I'm going to subtract off the stuff below 0.81, whatever I find from the table. So let's set that up right away. Now, drawing the picture, like I said, really helps with this because it makes you kind of figure this out. That when you go then to 0.81, right here, we have 0.8 and then 0.01 in this column here. We can see that the area that falls below that z statistic is 0.791. 0.79103. So the area below is 0.79103. That's this stuff over here. We can't forget that, wait a minute, that's not my p-value. That's not what I want. I want the area above. So if I subtract that from 1, I'll get 0.20897. And this is my upper one-sided p-value. That's what I'm looking for here. Now, the very last one, this is the one that gives people the most trouble, is this two-sided test, the not equals. The thing is that this isn't so hard. We're just saying, hey, we don't care if it's less than or greater than. We want to know if it's just different than. So it might be either of those things. So what we need to do is, it's a two-sided test, and the two-sidedness is important to remember because it means that we're looking at the two sides or the two tails under our standard normal curve. So let's draw this guy again. And we first put in our test statistic 2.34, that's our z-test statistic, and we want to shade in the area that is more extreme than that, under the tails. Well, here's the thing, it's two-sided, so we have to make this a symmetric area. What that means is that we're also going to go down to negative 2.35, or 34, excuse me, and shade in the area below the negative of our test statistic. Now here's the thing, these two areas, they're going to be the exact same thing because the z distribution is symmetric. So if we find one, we've found the other one. So you get to choose which one you find, but I'll prove that to you that these two areas are the same. Let's find this area first. So we're looking at the probability that z is less than negative 2.34. And we want to add that to the probability that z is greater than 2.34. Okay. So we know from the previous example that if we want to find this guy, we need to say, okay, I have to go 1 minus the probability that z is less than 2.34, and that should give me that probability. We know that these ones, when we're looking up the less thans, these are easy because that's the ones that the z table already gives us that. So the area below negative 2.34, we can go right back to our table. We go, okay, we see negative 2.3. We cruise over until we get to that 0.04 hundredths place column, and we have 0.00964 as one tail. So here's the confusion. People are like, I'm done. That's my p-value. No, that's not quite right. We have to add the other side. Now, I guarantee you it's going to add up to this exact same thing, but just for a moment, bear with me. We go back to our table, and this time we want to find 2.34, the positive. What's that area under this? And it's 2.3. We cruise over until we find the fourth 0.04. And that's 0.99036. You're like, wait, you said it was going to be the same thing. It will be. That's all the area below 2.34, and we wanted to find the area above. So stick with me. We'd go 1 minus 0.993 Hold on, what was that number? 036, that's what I thought. Okay, there we go. And this is, of course, 0.00964. So these two areas are exactly the same. And when we add them together, what do we get? Well, we get 0.01928. That will be our p-value. So this is how we find a upper one-sided p-value, a lower one-sided p-value, and a two-sided p-value. For any z procedure, this will work. Again, the p-value follows the direction of your alternative hypothesis. Also remember, drawing the distribution, super helpful. And remember that your z-table or software is always typically going to give you the area to the left of whatever you plug into it. So sometimes you need the area to the left, but sometimes you need the area to the right, and sometimes you need both. So keep that in mind, draw your pictures, and keep on at it. Hopefully this video will help you find p-values from here on out.